This is an introduction to the theoretical background behind smart subtle infinity in the context of collaborative clinical trials negotiations. The focus is on two core algorithms: maximize the minimum gain and visual blind bidding. Clinical trials negotiations often involve many parties and many issues. Here, a pharmaceutical company is negotiating a budget and a host of other issues for clinical trials research with a hospital. Each party would like to achieve 100% satisfaction on every one of these issues, but that goal is unrealistic. Traditional issue-by-issue negotiations are distributive by their very nature, and 50% for each party is the default expected outcome. However, with the help of some special algorithms, we can actually do much better. To see how, let's first rearrange these scales and reframe the problem in two-dimensional satisfaction space. Now, with hospital's goal at the top left and pharma's goal at the bottom right, we can plot the previously imagined scenario right in the middle and see that there is potential for improvement. In the movie A Beautiful Mind, Nobel laureate John Nash said that there was a theoretical limit to what negotiators could achieve, but that they normally fall short at the Nash equilibrium. Nash also explained that collaborative negotiators could find a route beyond the Nash equilibrium with his algorithm maximize the utility product. Some time later, Thiessen received a challenge from his major advisor at Cornell University, and, unaware of what Nash had discovered, Thiessen invented an approach with an algorithm called maximize the minimum gain. Thiessen's method can uncover hidden value among decision makers with conflicting objectives by taking them from a baseline to a fair and optimal outcome. Thiessen's research predicted 16% gains for each party in a certain class of two-party problems. Shortly after Thiessen published this work, Harvard professor emeritus Howard Rafa, considered to be a leading expert in the field of negotiation analysis, published his preference for Thiessen's approach over Nash's algorithm. Excitement was in the air, but it wasn't long before other researchers demonstrated that negotiators become very attached to their agreement after a tedious negotiation dance that has exhausted them in reaching it. Thiessen's new challenge was to find a way to overcome this face-saving illogic and reluctance to search for something better. Further research gave rise to an early intervention algorithm called visual blind bidding. Visual blind bidding requires negotiators to first build a single negotiating framework, which is like the final agreement, except for blanks representing a package of unresolved issues. Decision makers then model the problem and their preferences in such a way that comprehensive packages can be rated. Parties can then easily determine which packages meet their minimum satisfaction criteria. Preference analysis determines how parties become satisfied on each issue and helps an intelligent neutral site on the internet learn how everyone can become satisfied. This enables parties to exchange proposals as complete packages and shows smart subtle how to generate intelligent suggestions. Visual blind bidding invites parties to make secret bids on these suggestions. A mutually accepted package results in a deal. The process also prepares negotiators to maximize the minimum gain and thereby guide the parties to a fair solution that maximizes their mutual satisfaction. The process you've seen here can be extrapolated to negotiations with many parties. In concert with visual blind bidding and other algorithms, the smart subtle process is now practical in its ability to uncover and fairly distribute hidden value in a way that conserves decision-maker energy. The smart subtle neutral site embodies a total of 8 algorithms that are aimed at converting adversaries into collaborators and can virtually guarantee an optimal outcome for those that are willing to be guided towards that end.